All right, and now today we're talking about formants. Woohoo! Formants! So, how this is going to work is I'm going to explain to you guys real quick just a bunch of different ways we process a sound before we extract formants from them. And I wanted to show you this just to really show you the whole process, but don't get too caught up in these like early on details, like this page, this page, this page, this page, this page, aren't the relevant parts in regards to understanding exactly what formants are. They're just relevant for understanding the whole process, like the process as a whole. But this is the page where like formants really come in strong. So I just want to like emphasize that, and I'll remind you again when I get over here. But I just want to emphasize that these first few pages are not extremely and crucial for understanding what's going on. Anyways, so the first thing we're going to do, we get our sound signal, and we're going to remove all the high frequency components with the anti-aliasing low pass filter. And that's a big fancy word, but essentially what it means is we're preventing aliasing within the formants. And a good way of noticing that there's aliasing going on is if our formant frequencies, say like F1, F2, F3, grow like are like very close to each other for some reason. Like let's just say F1 is like 1000 hertz. Like if F2 is like 1001 hertz, like we know something's going on. There's probably some aliasing. Yeah. Anyways, so all that we're gonna do is essentially use convolution to basically get rid of any parts of our signal that are above a particular cutoff frequency, which is typically 22.05 kilohertz, because due to the Nyquist theorem, which simply states that whatever our sampling signal is, we shouldn't have a frequency whatever our sampling rate is, we should not have a frequency within our signal that is more than half of that sampling rate. So if we have a sampling rate of 44 kilohertz, for example, we would only want we would want frequencies only up to 22 kilohertz. Anyways, that's what this is for. Moving on. Our preemphasis. So this is the part that's unique to acoustic processing. So there's something called a 6 decibel roll-off that essentially means that our voice, the human voice, prioritizes lower frequencies. It gives more energy to the lower frequencies. And what we want to do to get rid of that is we want to emphasize the higher frequencies a little bit more. Sorry, I don't mean to get rid of the lower frequencies. I mean like even out the distribution of energy a little bit more than our voice does, because our voice heavily favors these lower frequencies. So we want to give those higher frequencies a bit of a boost. Anyways, so what we're going to do to do the preemphasis is we're going to try to construct a discrete signal based on our sound signal, x of n. So x of n is like the signal that we have, and y of n is going to be the signal that we're trying to construct. And what we're going to do is we're going to use a linear combination between just our sound signal and a time-shifted version of our time signal, x to the n minus 1, that is multiplied by a coefficient. That coefficient I will explain later. But basically, we're just going to use this to emphasize our desired frequencies. Okay. Now, to get into how we're exactly doing that, we're going to put this function in the z domain, the complex number domain, and make use of a little nifty property I have explored down here, where if we have a translated version of our function, x to the n minus 1 right here, we can rewrite it in the complex domain as x to the z multiplied by z to the power of minus 1, where z is a complex number. Now, what's crucial about this is if we notice x of z is the same as what x of n directly translates to, which is good for us. And x of z is simply going to be a summation of our original function multiplied by a bunch of different taken as a linear combination with a bunch of complex numbers. So let me say that again for simplicity. What we're doing to reconstruct x of z is we're taking our original signal and we're multiplying it so like it'll be like x of 3, z to the minus 3, where z is going to be a complex number, right? And we're going to be adding like x of 3, z to the minus 3 plus x of 4, z to the minus 4, etc., right? So we're taking a linear combination here to reconstruct our signal using complex numbers, and that is what x of z is. Okay, moving on. Sorry, I don't want to get too caught up in the weeds here. But what we're going to do is I sort of showed over here how to get an intuitive sense for what's going on with these very badly drawn graphs. So let's pretend this red frequency here, like on top and on the bottom, is x of n. And this frequency, the signal, sorry, on the bottom, I want you guys to see that as like the original a part of a lower frequency part of our original function x of n, right? And this top red part is a higher frequency component of our signal x of n, whereas the blue is going to be this function here, right? It's going to be that higher frequency component, but it's going to be shifted a little. And this blue down here is the shifted version of the lower frequency component. And yes, there's a coefficient here that leads to some scaling, but let's just not worry about that too much for now. So what I want to emphasize here is when you have a high frequency like this, if you add it to just a time shifted version, there isn't going to be as much destructive interference as if you were to do this with a lower frequency, if that makes sense. So if you notice this blue, when I shift it just a little, with higher frequencies, if I use just a small time shift, typically, I'm gonna wind up moving so far across so many periods that there won't be that much destructive interference. Whereas with our larger frequencies, when I do that little time shift, I might end up actually moving just half the wavelength. Wavelength over 2, half the wavelength, and creating more destructive interference. Anyways, what I'm trying to say is that this expression can help get rid of those lower frequencies. Now, another way we can look at this is by looking at the transfer function. So all that we did was just divided our function here by x of z, if that makes sense. And we're gonna change this complex number into its exponential form here to get a new function of frequency for our transfer function. And what we're gonna do is we're going to take just like with any complex number, we're just going to take the magnitude of it. Because cool things happen when we take magnitudes of complex numbers. And the cool thing that's going to happen here is, we multiply this out, we FOIL this part, we end up with this expression. There's this mathematically optimized value for this coefficient a here, 0.97. What this coefficient is going to do is it's going to result in this equation down here. Now, what's beautiful about this is, if you notice, let's just say we have like 0 in the argument of cosine here, right? Cosine of 0 is 1, and what will end up happening is all of this will cancel out. Well, what that's supposed to simulate is what happens if we have a really small frequency. Well, if we have a really small frequency and the transfer function goes to 0, then that means that we are essentially diminishing small frequencies from our function. On the other hand, larger frequencies, again, will likely be within like such a range that we're not coming back around the unit circle to get 2 pi in here again. It'll be like some ratio of 2 pi, such that there'll still be like some value here for h of f. Long story short, it'll keep, even with bigger frequencies, it'll keep those values or emphasize those values, but it will for sure. Because of what will happen towards smaller frequencies, it'll for sure get rid of those smaller frequencies. And I also want to emphasize here that this frequency here, because we're in the z domain, while it's definitely correlated and related to the frequency of your voice, like this won't be like 200 hertz or like 400 hertz, or anything close to what the human voice can be. Rather, it'll be something like on the unit circle between 0 and 2 pi. And it likely won't even get to 2 pi. Anyways, moving on. Preemphasis. We got rid of those higher frequencies. Okay, now what we're going to do is we're going to recreate our discrete signal and try to resample it so we have more of a continuous picture. Now, I want to mention here that even though we're reconstructing like a like a continuous signal. I'm sort of explaining the math behind it, but obviously because it's a computer and because it's real data, it's still gonna cheat a little. And basically what I'm trying to say is what we're reconstructing is rather than a full-on continuous signal, we're creating a discrete signal that just has slightly better resolution. But what we're gonna do is we're going to take the original sample, and we're going to take a bunch of sine curves using the sinc function here. And the sinc function is, I describe it over here, right? So this summation is going to create this this blob, this blob right here. That's basically just the sine of pi multiplied by t meaning time, minus, and this is n of t, capital T being the period, which I'll explain what that means in a second. But because we're at the beginning, n equals 0 right here, right? So this is 0, and then here n equals 1, which is why this is t, or yes, large capital T for period, etc. What we're basically doing is we're using our original, I say original, but we're using this discrete signal that we have created over these last couple pages to modulate a bunch of sine curves, a bunch of normalized sine curves. We normalized it right here. To reconstruct our signal in a more continuous fashion. And tau. Okay, or sorry, not tau. This capital T here. I also noticed I cut out because I noticed I forgot how to divide 1 by 50. Anyways, apologize. Praat uses 50 hertz, which is not the optimized value per se, but it's a value that engineers have found adequate enough thus far. But basically, Praat uses a resampling rate of 50 hertz, or in a period, a subsequent period of 0.02 seconds, to use to determine how many sine curves are used to reconstruct your signal. So let's just say your sound signal is 1 second long, right? That means that we're going to use 50 sine curves just to reapproximate that 1 second, and obviously it's this number is correlated like the Heisenberg uncertainty principle, right? Like if I try to get a lot more resolution with the sine curves, I'm going to end up losing some of the data due to smoothing, right? So there's a trade-off, but 50 hertz is sort of the optimized value that they found works for this trade-off. Sorry for cutting out there. Sorry, what I was trying to say was Praat uses 50 hertz, which is I also noticed I cut out because I noticed I forgot how to divide 1 by 50. Anyways, apologize. Praat uses 50 hertz, which is not the optimized value per se, but it's a value that engineers have found adequate enough thus far. But basically, Praat uses a resampling rate of 50 hertz, or in a period, a subsequent period of 0.02 seconds, to use to determine how many sine curves are used to reconstruct your signal. So let's just say your sound signal is 1 second long, right? That means that we're going to use 50 sine curves just to reapproximate that 1 second, and obviously it's this number is correlated like the Heisenberg uncertainty principle, right? Like if I try to get a lot more resolution with the sine curves, I'm going to end up losing some of the data due to smoothing, right? So there's a trade-off, but 50 hertz is sort of the optimized value that they found works for this trade-off. All right, moving on. Okay, now we're